All right, in this video I'm going to be working Linear Algebra Homework 3.2 and doing some examples of problems that deal with linear independence of a set of vectors. All right, so the first one is use the vectors above to determine if the set is linear independent. Okay, so we know the steps to take for that. The first one is v1, v2. Okay. All right, I'm going to just copy v1 and v2, 1, 2, 2, 3. We're trying to determine if the set is linear independent or linear dependent. So we're going to turn it into a matrix, augment with the zero vector, and row reduce to figure out the solutions to, like, how can I combine these to get 0. And I'm looking at these and I can tell, you know, because I've done a bunch of these problems before, that these are going to be linear independent. But I'll let you get to the point yourself where you can just look at these and make that determination. So 1, 2, 2, 3, 0, 0. Okay, that's going to, I'm going to subtract 2 copies of row 1 right here, so I'll have 0. And then when I subtract 2 2's, I'll have 3 minus 4 is negative 1. Whoops, just went under. Thought I had it perfect. Okay, now I'm going to divide this by negative 1. So I have 1, 2, 0, 0, 1, 0. And then I'm going to use this 1 to kill off that 2, and I'll have 1, 0, 0, 1, 0, 0. I'm going to interpret my solution space. This means that x1 equals 0 and x2 equals 0. But what are we even talking about here? What is x1? What is x2? x1 and x2 are the numbers of each of the vectors that I have to add together to get this one, right? The number of each of the columns I have to add together to get this. So I need to take 0 of this one and 0 of that one to get that. So if the only combination of these that gets the 0 vector is 0 of each, that means linear independent. So I'm going to say independent. Let's move that on out of the way. Second one is S is V1 and V5. I'll probably move a little quicker through this one. Okay, so S is the set that has 1, 2, and 3, 6. What I'll tell you is I can tell you for sure this is going to be a dependent set. But, you know, the reason why I can look at that and tell that, I think that's something I want you to come to on your own. So I'm going to turn this into a matrix. Row reduce to find the solutions to this system, really how many of this one plus how many of that one equals this. Okay, so I'm going to row reduce. I'm going to take 2 copies of the first, subtract it from the second. Okay, I've got that. Now I need to interpret my solution space. I'm going to do that by saying, okay, x1 plus 3x2 equals 0, which leads me to believe that x1 equals negative 3 of x2. Okay. Now, if I choose x2 equals 1, I'm going to have a non-trivial solution. Okay, so x2 equals 1, x1 equals negative 3. So basically, negative 3 of x1 plus 1 of 3, 6 equals the 0 vector. Oh, that's true, right? You guys see that? Okay, it said, if it's dependent, express 1 as a combination of the others. Well, I'm just going to say this one is 3 times that one. Okay, I'd say, you know, what is it? V5 equals 3 times V1. Okay, and maybe one of these next few will be a little more specific to where I have to do a little more work to figure out what that's going to be. But, you know, we'll deal with that when it comes up. All right. Oh, this was not number 3. Okay, pardon me. This is 1C. I hope nobody was confused, was scrolling ahead to look for where I was doing number 2 and then saw that that was not the problem you were expecting. That was 1B earlier. Okay, 1C is V1, V5, V4. All right. Oh. I'm not even going to copy these, copy the numbers, or even look at the numbers, because I know that all the V's are 2-dimensional vectors. And if I have 2 3-dimensional vectors, okay, and I'm just going to say dependent because there's 3 2D vectors. And if you have too many vectors for the space you're in, it's going to be dependent, for sure. And I'll show you how I can cook up a combination of these. I'm just going to take one of, let's see, let me actually look at this, be a little smarter. Hold on, V1, V4, and V5. I'm not seeing it. I mean, I'm pretty sure there's something I can, I'm don't forget, take V1, V4, and V5. Oh, V1 and V5 are proportional. That's why I wasn't seeing it. Okay, so what, -3 V1 plus 0 V4s plus V5 equals the 0 vector. That's it. So now I'm going to do part D. All right, 1D. And that's U0, U2, and U5. All right. So that's 1, 0, 0. 1, 2, -1. U0, U2, and U5. That is not U2. That's too bad. All right, so 2, 1, -3. Okay, so I was just wrong on all of them. All right. 2, 1, -3. U0, U2, U5. 1, 1, 0. All right, so what I'm going to do is kind of squash these together into a matrix to try to figure out how many of this one plus how many of that one plus how many of the other one I can add together to get the 0 vector back. 1, 0, augment with the 0 vector, and have at it. All right, first things first, turn that into a 1. In fact, I'm going to just divide row 3 by -3, and I'm going to use that as a 1. That's a pivot, and I've got all zeros over here. So I'm going to use this 1 to clear out that whole column. So I get 1, 0, 1, 0, 1, 1, 0, 1, 0, and of course I'll have just zeros on the right side because there's no way I'm going to have anything else doing elementary row operations there. So what am I thinking now? So, oh yeah, I'm going to use this one to clear out that column. I was supposed to have this one already cleared out. Yeah, pardon me. Right, I took this one, I subtracted 1 of them here, I subtracted 2 of them there, and that's going to clear out that column. Now, this is a pivot. I'm going to use that to clear out this column, and I'm going to just do that without writing a new one. And, well, hold on just a second. Heard some noise in the hallway. Okay, so I am having x1 equals 0, x3 equals 0, x2 equals 0, right? We could do a row swap to get this in fully reduced echelon form or whatever. But x1 equals 0, x2 equals 0, and x3 equals 0. Okay, there were 3 vectors, so if I have to take 0 of each of the 3 to get the 0 vector, I know that this is a linear independent set. Okay, there's another one. It's part E, U1, U4, U5. Oh, okay, I can see that. I can see that this one's going to be dependent because U4 and U5 are proportional. Okay, get that out of the way for you. 1E is going to be, and if you see that, you feel free to say it's dependent because you know in your heart that it's dependent because you see U4 and U5 are proportional. That's completely fine. Okay, U1, 4, and 5. 1, 2, -1. 4, 4, 0, and 1, 1, 0. All right, so we're going to test this for linear independence. And maybe you've been wondering, like, wait a second, if the columns are proportional, how's that going to play out in terms of the row operations? Because these are row operations. How am I going to induce a full row of zeros? And it's an interesting thought. What we're going to do is we're going to turn this into a 1 and use that to clear out that whole column because everything else is zeros. So I'm going to go over here. I'm going to say 0, 0, made that positive 1, 4, 4, 0, 1, 1, 0. Still zeros over here. Whoops, pardon me. Should double checked. Now, I'm just going to take this one and subtract it from that one, or whichever way you want, right? Regardless, I will have one row that has a 0, 4, 1. I'll have this thing also, and then I'll have an all 0 row. Okay. Now, I'm kind of trying to get this in fully reduced echelon form, so I'm going to row swap up here, and I'm going to have 1, 0, 0. I'm going to divide this by 4, 0, 1, 1/4. And this is still a row of all zeros, and nothing we're going to do, change that. And there we go. Okay. Now I'm going to interpret my solution space. Because it's not always the case that if you see a row of all zeros, that it is necessarily linear dependent. In fact, I know it's not on the homework, but I'm probably going to just cook up a set of vectors that I'll show you as linear independent, despite having a row of all zeros at the bottom when we fully reduce it. Okay, so x1 equals 0. x2 plus 1/4 of x3 also equals 0. So x2 is negative 1/4 of x3. Okay. If I choose x3 equals, let's say negative 4, then x2 is 1, and x1 has to be 0. Okay. And oh, I really liked this. We talked about this example in class, and I really like this one for a couple of reasons. Okay. First of all, we can really see with the negative 4 and the 1 how we would add a linear combination of these together to get the 0 vector, right? Shouldn't, what is this? U1, U4, U5. So none of U1 plus 1 of U4 minus 4 U5 is equal to 0. Okay? That's me exhibiting a combination of the vectors that gives the 0 vector. But I also want to say something about why does x1 have to be 0? That's not something we've seen in the past, right? Usually, like, it's just in terms of one of the vectors. But u1 is fixed at 0. And if you think about u1, or x1 is fixed at 0, so I have to take 0 of u1. It's because of this negative 1 right here, right? If I take anything besides 0 of these, and I add it to these, there's no way I can get back to 0. So I have to take 0 of the whole thing just because of this third component. And so that's, something that's worth thinking about. Okay. Before I move on, I'm just going to call this 1F, I think. I'm going to show you an example of 0 row but not linear dependent. I think this would be a pretty easy situation, right? Like, we'll be able to reduce this real quick. So we squash it together in a matrix. Figure out where we can combine it to get 0. Take that, I turn it into a 1, clear that out, and I get 1, 0, 0, 1, 0, 0, 0, 0. And that means that I have x1 equals 0, x2 equals 0. You might be thinking about, what about x3 and x4? What does that even mean, right? The x's are how many of each of the columns do I take to get the 0 vector. There's only 2 columns, so there's only 2 variables. Okay? But even though this has row of all zeros, this is a linear independent set. Okay, just figured I'd throw that out there while you were watching. Since you showed up to watch the video, get some help on the problems. All right, now the real number 2 is determine conditions on the scalars so that this set is linearly dependent. Okay, here I only have one scalar. So this is really, I'm just going to row reduce and hope to, unless I don't really see anything. Wait. Okay, if you take the first vector and you add it to the third vector, you'll get 1, 3. And if A is 1, this will work, right? But there are going to be more than just that, I think. I hope that I don't go do all these steps and find it was just A equals 1. Honestly, I am not sure if that's how it's going to play out, so I'm going to run through it all. On the next one, I know that there's an easy way to find one set of values for A and B that works, but they are not unique because I've already worked that problem. I have not worked this one yet. Okay, so I want to figure out, if this is linear dependent, so I'm going to just going to row reduce it. I'm not even going to augment it with 0 because I'm just going to talk at the end about what would need to happen or what would have happened if I'd augmented with 0. All right, so I'm going for 1, 0, 0. That's my goal. So I'm going to subtract 2 row 1s from row 2 right here. So 2 minus 2 is 0, 3 minus 2 is 1, 1 minus 2 zeros is still 1. Right, this is still a 1, 1, 0 situation. 1, 2, A. So I'm subtracting 1 of row 1 from right here. So 1 minus 1 is 0, 2 minus 1 is 1, and then I'll have A minus 0. Okay, that's nice. Okay, I feel like A equaling 1 is going to be necessary here, but I'm not 100% sure that's how that's going to be the only answer. Okay, I guess I'm going to subtract row 2 from row 3. Yep, that's exactly what's going to happen. Okay, so it's 1, 1, 0, 0, 1, 1, 0, 0, because I'm subtracting, and I'll have A minus 1. All right, yeah, I think I'm good here. If I had augmented this with the 0 vector, I'd still have a 0 out here. And so maybe I'll just say, okay, envision I do have it augmented with zeros. If this thing is going to be dependent, it's because this equation has infinitely many solutions. So we can't have 3 pivots. That's not going to work. If this is not 0, then I just divide this row by whatever it is that's not 0. This turns into a 1. I clear that out. This becomes a pivot. I cleared that out. So then I'd only have the 0 solution, only the trivial solution. So it would be independent. So I need A minus 1 to equal 0, which is A equals 1. Okay. I think that was worth the check just to make sure that there weren't other non-trivial solutions. Okay. 2B is a little more complicated. I'm going to budget myself more room than that. So I'm going to start at the top of a new page, and I'll say this is 2B. Okay. So the set is 1, 2, 1, 1, A, 3. And 0, 2, B. All right, and this I'm going to just, to avoid confusion, in case there's any kind of 6 in this matrix, I'm just going to use capital letters. Just so you, the viewer, you know what I'm doing. So I have to slow down and be super careful about my penmanship here. Just do algebra. So, hold on. Let's see. Yeah. All right, I'm going to turn it into a matrix, row reduce it, just like I did with the previous one. Okay, what I was thinking was that if we doubled this row, we could set these things equal to each other, and we could have an example of values of A and B that worked. Those were the ones I saw. Some of my class saw a different combination. And then once I saw that there were 2 combinations that it wasn't obvious, like, oh, they both, A and B have to multiply together to be 12 or something like that. It wasn't that, so I figured we needed to row reduce, and then I found, some interesting stuff happening. So I'm going to subtract 2 copies of row 1 from row 2 and subtract row 1 from row 3. All right. Okay, so I'll take A minus 2 times 1. And then 3 minus 1 is 2. Okay. Then I think I took 2 minus 2 zeros is still 2. Then over here I took B minus 0, and no, that's still going to be B. Okay, and then I'm going to, what am I going to do here? Hold up. Lost it. Oh yeah, I need to get, I forgot what I did in class. Can't remember if I divided this by 2 or if I divided this one by A minus 2. Let's divide this by 2. I think that's what I did in class. It doesn't matter. It's the exact same. It's going to play out the same way. For me, I'm more interested in, that's a 1. And so this became a half of B and 0. And that's still a 2. I did not do anything to row 2. Okay. So now I'm going to, and this is like not obvious enough that I'm going to just kind of copy it in. I'm going to, and special thanks to 216, who is actually a calculus student, who gave me a nice new pen today. I don't know what for, maybe just because he's a nice guy, but I do really appreciate it. So I'm going to take row 2, and I'm going to subtract A minus 2 copies of row 3. Okay, I thought this was going to be a different colored pen than black. Okay, that was a letdown, but it's all right. Still appreciative. And, okay, you did it like that. Okay. I'm going to do that, and go back to my felt pen, and I'm going to take, okay, so that's going to kill that off. So row 2 minus a minus 2 of row 3. Okay, so that's 0, 0, both of those. I think I had a 1 up there, yeah. I'm still having a 1 up here. I'm still having a minus 2 and 2. And, okay, pardon me, row 2, and I subtracted. Okay, that's going to be a bit messy. Okay, so if I'm subtracting a minus 2 from a minus 2, I'll have 0. This is still going to be b divided by 2. And I'm not going to box myself in there. Okay. Now, this is going to be, if I take a minus 2 copies and subtract away from this, it'll be 2 minus a minus 2 copies. That was supposed to be a 2, not a 1. A minus 2 copies of row 3, which is b divided by 2. Okay. Now, in order for this to be a dependent set, I need this to be all 0. Okay, because then I'll have non-trivial solutions when I augment it with the 0 vector like that. So I need 2 minus a minus 2 times b over 2 to equal 0. And they just ask for conditions on a and b. So you'd be perfectly fine to stop there. I'm going to solve for a and b in terms of the other just to show you what that would be. All right, so I'm going to say that 2 equals, and I'm going to distribute ab divided by 2 minus a b. Okay. So if I think over here I need to be solving for a. If I was to distribute, if I was trying to solve for b, I'm going to actually go back up here and just solve for it that way. Okay, so I'm going to say 2 plus b equals ab divided by 2. Okay, so I'm going to double it. 4 plus 2b equals ab, and a equals 4 plus 2b over b. That'll be good enough. And then b, if I was trying to solve for b, I'd just try to get at that thing. I'd probably add it over, divide by the a minus 2, and then double. So what I'll have is 2 equals b over 2 times a minus 2. I'm going to multiply by 2, and I'll say 4 equals b times a minus 2. And then I'll solve for b, and I'll say b equals 4 divided by a minus 2. That's nice. Now, the last one is solve the equation fx equals u1, gladly. Okay, so f times x equals u1. Okay, so what I'm going to do is row reduce f augmented with u1, and I'm going to arrive at a solution, hopefully. Okay, so f and u1. Okay, so I'm going to say 1, 0, 0. F is 1, 0, 0, 2, 3, 0. And 1, 2, 1. This is upper triangular, so I know it's going to be pardon me, you don't know about non-singular quite yet. That was what we talked about in class today, so I think I just got a little ahead of myself. So u1, right, is what I'm going for, and u1 is 1, 2, negative 1. All right. Well, I'm going to use this one to clear off that, but I can't do it freely without any sort of consequences because I have to track what's going on the right side. But it won't be too bad. So I'll have 1, 0, 0, 2, 3, 0, 0, 0, 1, and this is a negative 1 still. That's going to stay that way. And what am I doing? I'm subtracting 2 up here. So 2 minus 2 negative 1s is going to be 4. And then I've got, what's going to happen? I'm going to subtract up here. And what am I doing? I'm subtracting 1, so I'm subtracting a negative 1. That'll be a 2. 1 minus negative 1. 2 minus negative 2 is 4. Okay, cool. I'm good with that. All right, 1, negative 1. Okay, I need to deal with that business there, so I'm going to have 1, 0, 0. If only. But I'm dividing by 3, right? It's not going to be 0.75. It's going to be 4/3. I don't really like dividing by 3, but that's okay. So that's going to be 4/3. Now I'm going to subtract 2 of these from this. Actually, I'll just copy it so I don't leave anybody confused. Now I'm going to subtract 2 of row 2 from row 1. So it's going to be 2 minus 8/3, which I think is going to be negative 2/3. So I'm subtracting 8/3 from 2. 2 is 6/3 minus 8/3 is negative 2/3, 4/3, and negative 1. Okay. You can check my solution if you like. And definitely let me know, send me an email, let me know next time you see me in class, or just leave a comment below if that is not the right solution. But that's going to be all for this video.